In order to determine how the second configuration of the product fructose bisphosphate is derived, we need to focus on the nucleophilic portion of the molecule. That's the enamine structure shown here. The new configuration is going to derive from this prochiral position that is shown here, and basically what we need to determine is whether it's the top face of the enamine that attacks the aldehyde, or is it the bottom face of the enamine that attacks the aldehyde. In both cases, I'm showing you the psi face of the aldehyde, since we already know that that's the face that must be attacked, and what we're going to do is go through this analysis, looking first at the top face attack and then at the bottom face attack. Before I do that, let me just say that we're making an assumption. I'm giving you an assumption. We're assuming that the configuration of this carbon-carbon double bond of the enamine is trans. I'm assuming that the hydroxyl group is on the opposite side of the nitrogen, and if that weren't the case, then the stereochemical analysis would be switched, and so I must give you that piece of information. I must tell you what the configuration of the enamine is in order to go through the analysis and say, is it the top face or the bottom face? Alright, let's assume that this is the configuration, and let's do the top face attack, and we're going to leave the hydrogen atom as a point of reference. We're going to leave this hydrogen atom in the plane, and we're going to rehybridize, change the geometry here from planar to tetrahedral. If the attack is on the top, then the new carbon-carbon bond is this bond here, and the hydroxyl group will have dropped below the plane. So this tetrahedral carbon now has a hydroxyl group below the plane, and the new carbon-carbon bond, which was derived from the electrophilic carbon of the aldehyde, is on top. Now I need to redraw that, and you should try to reorient this molecule that's drawn in the plane to the planar projection that's shown over here on the right. The atoms that are in the plane are highlighted there, and so starting with the phosphate, you can see that these atoms were all in the plane, and so all I've taken is that molecule that was drawn with this perspective view in the orange plane and put those atoms in the plane of the paper. And so what I can see is that this position must represent the group that's pointing outward, and that's the carbonyl, that was the carbonyl of the aldehyde group. That's the new carbon-carbon bond, and in the back must be the hydroxyl group. And so that's what I can imagine as I took this perspective view and rotated it in the plane that's shown there. Indeed, that's the way it's positioned. I just need to do a conformational rotation in order to put this bond, because the way that the product fructose bisphosphate was drawn in the previous webcast was to have all of these atoms in the plane, and so I need this atom of the carbonyl, what was the carbonyl of glyceraldehyde 3-phosphate, to be in the plane. When I do that, then the carbon will occupy this position, the hydrogen will occupy this position, and then the hydroxyl group will come out toward us. And so the new stereocenter is that the hydroxyl group comes out toward us, and we need to think about whether that matches the product or not. Before we do that, let's go ahead and do the bottom face addition. I'll take you through that fairly quickly. The bottom face addition changes the geometry here. Since we're doing bottom face addition, the carbon-carbon bond is going to be below. We're going to have the hydroxyl group above, and we're going to keep this hydrogen atom in the plane. That's our reference point. Now, we redraw the atoms that are in the plane, starting with the oxygen of the phosphate group, ending with the hydrogen atom. There they are, and now we can see that this position must be the hydroxyl group coming out as we've rotated that perspective into the plane of the page. And if you can't see that, I would encourage you to build a model. We need to do a conformational change to put all the carbon atoms in the plane, and when we do that, this carbon atom is going to occupy the position of this hydrogen, and so we're rotating in a direction in order to bring this carbon atom up to that position. The hydroxyl group will end up going into the back, and the hydrogen atom will end up coming out here. And so the hydroxyl group will be in the back, and indeed that's the geometry that we have after that conformational change. If we look at the position in fructose bisphosphate, remember that it's drawn with a dashed line. That hydroxyl group on that position, you can see we've matched the V down, so there's the 3 atoms down, and we have the hydroxyl group going to the back, so the attack must have been from the bottom face of the enamine. And so that's the conclusion that we reach with this analysis. So to finish up the mechanism, all we need to do is have hydrolysis of the aminium ion take place. And so here's where we left the mechanism off, right after the aldol reaction carbon-carbon bond forming step. Water is involved. The addition of water is going to be general base catalyzed. We'll do that addition. Basically all of these steps are the reverse of what you've seen before, and so we have a new tetrahedral center here. The amine group has now become protonated. There's going to be a proton transfer that's involved so that we can set up that lysine as a good leaving group, and now the lysine at 146 is going to be neutral and basic. It's going to be able to serve as a general base that can deprotonate the oxygen so that we can make a carbonyl and eliminate the ammonium group. That's exactly what happens next, and we've got our product released. The two amino groups in the aldolase enzyme have returned, one to be protonated, the other to be neutral, and the mechanism is complete.